Okay, so today I want to talk about directional derivatives just because I think it's something I've had trouble with. And this isn't the most challenging problem, but I think it'll illustrate, for my own sake, sort of what a directional derivative really is. So the directional derivative tells you how fast a function is changing at a specific point in a direction that you choose. So not just randomly, but along a specific path. So you can imagine that you're standing on a hilly surface and you want to know how steep the ground feels as you walk, let's say northeast. The directional derivative answers how steep is it if I go that way from here. So how is that different from the gradient? This is something that, I have just had trouble with. The gradient vector, from my understanding, points in the steepest uphill direction at that point. So it's like the steepest ascent. It's like a compass that always tells you which direction the steepest climb is, and the magnitude of that gradient tells you how steep it is. So the gradient is basically answering where is the steepest path and how steep is it, while the directional derivative answers how steep is it if I walk this way instead. So if your direction lines up with the gradient, you're walking straight uphill, and the directional derivative equals the magnitude of the gradient. And if you walk perpendicular to the gradient, the directional derivative is 0 because you're not gaining or losing elevation. So that would be the same thing as walking along a contour line with a constant z. And if you walk opposite the gradient, the directional derivative is negative. So you're going downhill, you're descending. So with that in mind, I want to go over this example. And the first step is we have to compute the gradient of f of x, y. So let's do the partial with respect to x, which would be 1 over 5x plus 4y times 5, which would give us 5 over 5x plus 4y. And then derivative with respect to y would be 1 over 5x plus 4y times 4, which would give us 4 over 5x plus 4y. And that gives us our gradient. So we can write it like this. And that's our gradient. So now that we know that, we can start to calculate the directional derivative. However, by definition, the directional derivative uses a unit vector direction. So we are given this vector, but we need to make it a unit vector. So we can do that. That's pretty easy. We can calculate the magnitude of it, which would be 6 squared plus 8 squared, which would be the square root of 100. Oh no, my Apple Pencil's dying, which would be 10. And so we can now make this a unit vector by dividing u by 10. So we get 6 over 10, comma 8 over 10. And so we're going to use this to compute the directional derivative, which is d sub u f of x, y is equal to the gradient of f of x, y times the unit vector. So because I'm lazy, I'm going to copy this here and copy this here, and we're going to take the dot product of these two, and we're going to get 30 over 10 times 5x plus 4y plus 32 over 5x plus 4y times 10. And so this is the directional, sorry, my iPad is messing with me. This is a directional derivative, and if we want to evaluate this at, what was the point, 3,9, we can simply just plug in. So we would get 30 over 10 plus 15 plus 36 plus 32 over 10 plus 15 plus 36, which would equal 62 over 510. And that's our answer. So that's telling us how steep it is if we walk in the direction of u.